Okay, so in this session 2 list, the virtual instrument I've shown you. Let's look at quickly at the first of these topics, which is software-defined radio. So the software-defined radio that TIMS implements is quite different to the many commonly available, either the small analog devices units or NI's USRP. We explode those complete SDR units where you have data in and RF out. We go to the heart of it in 2 ways. We have a module which runs GNU radio, but we operate at the heart, IQ in and IQ out. So this is at the very heart of the software-defined radio. And the software is actually on a USB. What we provide is we provide Linux Mint pre-installed with GNU radio pre-installed. So the student simply plugs this into their laptop or computer, they boot off this USB, and now they instantly have a Linux machine running. So there's no software to download or install or download from the internet. So we provide, our software-defined radio is the hardware and the software ready to run out of the box. So if I zoom in a bit closer, so the module, and you see this is not an SDR on its own. It uses other TIMS modules to build the communications experiment. Here's the software in the dongle. So now let me show you real examples. So here's one example, GNU radio modulator and TIMS hardware as a demodulator, showing students that SDR is not some abstract concept and it's all inside a magic box. What we have is we have an audio oscillator as the message. We have the SDR module running GNU radio, which is the FM modulator. We use a TIMS module, this one, the quadrature utilities, which has 2 multipliers and an adder, and that makes the FM transmitter. So now we use TIMS modules, an adder, an RC, and a VCO to build a phase lock loop to recover that FM. So you see we're mixing SDR and hardware to show students that they're producing the same signals. And down here you can see in this slide a quick image of what this experiment looks like. So the transmitter is on this side with the GNU radio here running the SDR module, and here are the 3 modules creating the phase lock loop. So with this, I won't go into the same detail with the other examples, where we have TIMS hardware modulator and the GNU radio SDR is now the demodulator for a QAM signal, and so on. So this gives you a very, very quick overview, an insight into when we talk about SDR, how this is really focused as a very educational, hands-on SDR approach. Does that make sense? Any questions? Next.
Yes, thank you.
Great. Next, very quickly, we have a DSP module. This is our 3rd generation module. It's based on TI's 6713 DSP and their DSK board, but we provide an add-on board which plugs in, which provides high-speed A to D and D to A, so that this is used in experiments such as convolutional decoding, trellis code demodulation, turbo coding, and OFDM. So that's where we use the TIMS DSP in these kinds of experiments. So, and there I wanted to show you this. So you can see that the TIMS DSP is used together with other modules to create these, and I'll show you shortly further examples. This happens to be a convolutional coding and decoding experiment. So next, you mentioned fiber optics. TIMS implements a range of fiber optics experiments. The fiber optics experiments are summarized here. So first of all, the electrical, optical electrical interfaces, both analog and digital signals, optical splitting and combining, bidirectional communication on a single fiber, and WDM. So what we have is, to show you, we have red transmitters, we have green transmitters. So you can see we're not using lasers here. We're teaching students the principles of optics. So this is not an industrial or a professional fiber optics lab with circulators and lasers and so on. Here the students can actually see the signals. So here we have an optical coupler, and you can see the fiber, the 1 millimeter polymer fiber we're using. So this coupler has 2 inputs, 2 outputs. So 2 optical signals can be mixed and go out the channel, or 1 channel signal can come in and the optical signals can be split. So we have these kinds of experiments, and of course we have the filters. So we have a red filter and a green filter. So with these core building blocks and the other TIMS modules, these are the kinds of experiments that TIMS can implement in fiber optics.
Yes, so there's a question here. So you have an experiment on losses in optical fiber. That is if I understand correctly, a new fiber. So this is pretty new because I haven't seen this one from TIMS, the fiber optics one. The last one, you have losses in fiber optical systems. So this can be maybe another course in optical fiber as an elective, maybe a little bit later. It can be an optic fiber communication. And I'm interested in the last one. So is that you have an experiment losses in optical fiber in fiber optical systems or optical fiber system? Yeah. So you have that's all different experiments. Yeah. Fiber optical transmission, optical signal splitting. Yeah. A little bit, just briefly, can you talk about the losses in fiber optical systems? So what is this experiment? So what type of modules you have for this one?
The losses, we're using the transmitter, we're using these couplers, and also these bulkheads where the students, for example, connect these fibers in different orientations, so they can see that the orientation of the connection actually changes. So they're all quite quantitative, where the students are actually measuring and seeing the different performances. So remember, what we're operating in is these couplers. So this is our environment.
Yes.
The couplers, the polymer fibers, the bulkheads, and the receivers. Noting that the receivers have both have an analog output. I'm just looking to find the receiver.
Because we are presenting to the students how to calculate the power budget. So if they can use this experiment to calculate the power budget in optical fiber system, so that you can simulate, the whole optical fiber system, this modules.
This is a step. This isn't. We don't do these more advanced power budget calculations. Here the student is looking at what the losses mean. Where do the losses come from? With this LED, bright LED environment. Okay, so yes, they make actual measurements on the original signal, the signal going through the system, and what are the losses in connections and so on. So the whole intention here is to introduce students to these concepts of why are there losses, bending losses, for example, and so on. So these are the different, broadly the topics where we're discovering, we have documented. So the fiber optics manual itself, I don't have it here, but I can send you a separate brochure which gives quite a detailed chapter, the chapter topics. The fiber optics manual itself is also some 300 pages of experiments covering this, and what we call the physics of fiber, polarization, as I said, bending losses, and different gratings and so on. So yes, we do cover those sort of concepts ready for the student before they go into the commercial fiber optics lab. So this is all the underpinning concepts.
Okay, thank you. Okay. Thank you.
Okay, the last one I'll cover in this section is expansion options, which are open to you, the professor or the student. So the first is a simple one, is an expansion rack, which adds another 12 slots and sits on top of the TIMS unit. So that's obviously used in more elaborate, much more advanced experiments. Most important is this project module, where we provide, when you purchase TIMS, you get access to our users-only downloads website, and there you have access to all TIMS manuals, including the project modules manual, which gives you all the dimensions and all the physical specifications for making these modules. And with that, you can either purchase this project module from us, or students as capstone projects, or professors sometimes as projects, can design their own circuit boards and make their own modules to use with TIMS. So TIMS really is an open-ended system. Some years ago, I did a survey of professors, and about 50% had created at least one module of their own. And I soon learned to ask the right question, which was, what was your area of research in your PhD? And it was some area of telecommunications. And most often the professors would create at least one module that would demonstrate some of those concepts that they were so familiar with from their own research. They would all say, oh, this is a really important area students should be exposed to. So TIMS truly is a modeling system and an open system, because you can absolutely make your own modules. So if we don't implement an experiment, if we don't have modules to create an experiment that you think is very important, that you want to expose students to, the system is open for you to do this. Next, just quickly, there is a large breadboard which has an inbuilt power supply and buffered inputs and outputs, so students can actually wire together circuits on the breadboard and interface them with the rest of the TIMS modules. So that covers these, the projects side of our experiments. So next, I'll just quickly move to okay. Okay. First of all, let me introduce these. No, I think to cover to cover, let me go through here. Okay. So this is what I was just talking about, projects. This happens to be a photo of a student from Sydney University who implemented, his thesis was to implement gold codes, which he designed in MATLAB, but then actually implemented them in TIMS to prove and measure their coding gains and so on to prove they work. I'll quickly skip through this slide. There are lots of quotations from users on our website. We have 4.5, we now have something like over 5,000 pages of experiments. I wanted to cover this. So sometimes we're asked, what does TIMS cover in wireless communications? Well, TIMS doesn't have a Zigbee trainer or a GSM or wideband CDMA or a 5G trainer. What we do is TIMS operates at the physical layer. For the OSI model, that physical layer and layer 1, what is at the heart of, what is the modulation scheme? For example, 4G systems, 5G systems would not function without OFDM. So what we introduce students to is the OFDM layer, that physical layer. What are the characteristics? How does it work? Why does it work? What are the characteristics? Or in IoT, we don't have an IoT trainer, but we go down to the physical layer and we look at the different modulation schemes that are used in IoT, whether it's ASK plus DSSS and so on, or ultra wideband, and what are the different. So we're looking at those modulation schemes at that physical layer so the students can see what is at the heart of that so-called wireless scheme and how it's functioning. So here you can see, for example, Bluetooth, and core of Bluetooth might be Pi 4D QPSK. So we don't have a Bluetooth point-to-point. We're looking at that physical layer, that what is the modulation scheme that actually makes that work. So this covers that aspect. The other aspect, which I just had on before, is for us, so what do we cover in 4G and 5G? So here we can see number of experiments, bit error rate measurement in 16 QAM modulation schemes as used in 4G mobile, and so on. So we're again looking at that physical layer. So here you can see examples of these experiments in 5G, the low density parity codes, LDPC, or the polar codes that are used in the systems, as well as something that we cover the OFDM, different aspects of OFDM. As you spoke earlier, we compare, for example, a QAM signal going through a multipath channel versus an OFDM signal going through a multipath channel. So we expand to that sort of level of at the physical layer of what's happening. So with our OFDM, if you just excuse me for a minute, I'll open another brochure that I didn't open previously. So our OFDM experiments. So we have, let me just skip up. We have 3 kinds of OFDM experiments. The first uses no DSP. We use 3 audio oscillators which are tuned orthogonally. So we have a 3 subcarrier OFDM. So the students can see, what's this DSP doing? What is all this IDFT stuff? So we actually break it down so the students can actually do simple experiments with the concepts of OFDM. And then our next level is OFDM using the DSP module that I just showed you previously. Again, the input is data, the outputs are I and Q, so we use TIMS modules to build this experiment. Below that is an example. So here, for example, is the multipath channel. For example, here you can see we have 4 paths. So each path the student can adjust the gain and the time delay, and actually then see the resultant effects, not just in the time domain or the frequency domain, but we also dig into the DSP at the receiver, and we show the students vector diagrams of the phase and amplitude of each subcarrier at the receiver. So as the students change the channel characteristics, they can see what's happening to each subcarrier and what this means, and hence apply equalization and then do bit error rate experiments on that OFDM signal going through a multipath channel. So that hopefully gives you a little bit of an idea of our range. And if you're more interested in these, we have a number of YouTube videos which actually go and demonstrate these OFDM experiments in some detail. So that's, let me see. So next, any questions before I move to the next? No? Okay, now I'm just going to quickly skip through because I want to cover these rather quickly and then do some more digital modulation experiments. So we do, for example, concepts such as frequency hop spread spectrum at, as I said, at 100 kilohertz, where the students can see these frequency hop signals. We have a whole range of CDMA and time hop spread spectrum experiments.